Hello, nice to meet you. My name is Cheng. I am right now CTO and co-founder of Sunday Robotics. And I have a few slides about myself. I started as an undergrad in University of Michigan. That's the first time I set foot in the United States. And I'm very fortunate to be advised by Dimitri Berenson from my undergrad. That's the first time I had research experience and I understand what it's like for academia. And then after that, I did my PhD with my lovely advisor, Shuran Song. We started out in Columbia University in New York City, and then I moved with her to Stanford towards the end of my PhD. During my PhD, there are two works that I really enjoy working on. One is called diffusion policy. Oier, I think, told me that you guys might have covered similar material. There's a lot of works similar to diffusion policy now. For example, I think there's people using flow matching. People use diffusion for video and action generation. People use diffusion for locomotion. Turns out to be used by quite a few people. And then my last work during my PhD was called Universal Manipulation Interface. I would say this is much more a hardware project than a software project. The code base is the same as diffusion policy, but the work's about this kind of open source, lightweight report that allows you to collect data without needing a robot. And I would say my life after PhD is much more about scaling this universal manipulation interface project than scaling diffusion policy project. Right now, so after my PhD, I met Tony initially on Twitter after the diffusion policy announcement. And then again, we got reunited at Stanford because Tony was also at Stanford. And then we started this company called Sunday Robotics. Today, I'm going to talk about this lecture is called Robotics Beyond Algorithms, where I'll talk about a lot of aspects that I learned after my PhD graduation. A lot of them are quite surprising to me, and it will be less so about generative modeling or traditional what I learned during my student times. But I wish I knew before coming to the startup. Yeah, when we look at a modern robotics company and robotic system, by modern I mean after I graduate my PhD, pretty much everything is focused around the policy. For different companies, it might be different. So for manipulation company, it will be like a visual motor policy or in academia as well. And then for works that are related to locomotion, this is often like a blind RL policy. And then still, we are, even though people keep saying about end-to-end, it was never actually end-to-end. There's always some software between the sensor and the policy and the actuators. There's a layer of robotic software, often uses various kind of classical robotic algorithms, from the simplest to like PID control to something more complicated like SLAM. And then I would say these two areas are usually what I during my undergrad, during my PhD. These are what I understand that these are called robotics, and fundamentally these are really robotic algorithms. I think they're very popular because I'm in the CS department. And these algorithms they're very fun, they're very interesting, and they're also very easy to teach because fundamentally, to implement them, it's just software. So you just clone a repo, you can run some scripts, it's very designed, homeworks around. But after, these are how I learned during for robotics about these aspects. So I learned these during classes. These are two of my favorite classes: Modern Robotics by Kevin Lynch and Interactive Robotics by Professor Russ Hedrick. These are, when I was in my undergrad and early days of PhD, I took a lot of these classes and it taught me about math, theory, and algorithms about robotics. And then during my PhD, robot learning became very popular, and then I started reading papers, and these are how I learned about robot learning. But I would say after graduation, I realized that these are only actually a small part of robotics, and there's like many other things, especially hardware and data, that's I would say very, very critical to get robotic system work. And I would say it's actually a very big differentiator between different works or between different teams. So first, I want to talk about hardware. And I want to use an example of like building a very simple component. Pretty much everybody need to use it at some point if you want to do robotics. Is a camera. So if I want to build a camera, like when I started the project, it will be like there's an analogy to when you're starting a software project. So in software, you'll probably let's say if you want to work on some generative model project, then you go Google search some repositories that is interested. You download the repository, and for hardware, really, it's rarely you want to start truly from scratch. So what you do is that either find open source hardware out there, or you go on Amazon, buy something similar, and you take it apart and see how it's made out. And often a very important step during this process is to find reusable components. For example, for the software project, you also often find a file called requirement.txt, or it's called something.conda.yaml file. You'll see a lot of dependencies. So you install NumPy packages, PyTorch, CV. These are almost like in every single project. And in the camera hardware example, we see that there's important components. There's a lens, there's a sensor, there's ISP. These have specific models. And then we know that if you want to build like a camera like this, you need these components. And in a software land, so like when you put all these components together, in a software land, we call this what I call requirement.txt. Really, this is a build instruction, or it's like a software dependency list. In hardware, the corresponding concept is called BOM, bill of materials. So on the right, I have a screenshot for part of the diffusion policy project. It's like what is the part you need to buy, what the quantity, there's a link to buy, and how much does it cost. And once you have this this list, you need to build your development environment. So in a software project, what I do is I do pip install, and so really that just automatically fetches all the packages to your local environment, so you can finally start writing code. And in hardware, this is actually much more complicated because these components might come from different vendors. The easiest thing is you can buy on Amazon, but sometimes things are out of stock. So like this is really this process is called procurement. This is like really bare bone prerequisite before you start any hardware project. And I would say this is kind of like how things end, at least for me for Umi. The reason is that, and then everything is actually working quite smoothly because all of my bill of materials are on Amazon. So it is something called a retail channel. That's something you can just click link and buy. And really, retail I think is pretty powerful abstraction. It creates an illusion of low latency, so you can get exactly what you want very quickly. And the reason and the entire business of retail is building this physical caching layer. So at where the customers are, you have these shelves or virtual shelves where you put stuff on, and then when people want it, they just grab it from this local cache. But really, this is an illusion of how the physical world actually works. If you want to change anything about any of these components, or if you want to order large quantity at a time, you either quickly exhaust these cache in the retail channels, or you will need to make your supplier or your suppliers to change something. So camera module is made of lens, PCB, and cable. And each component have their own supplier. So like lens supplier buy glasses, buy housing. The PCB supplier get like a design file for you, and then buy sensor, buy ISP, and put them together. Really, just everybody just in the business of buying stuff and putting things together and selling it. And this is what we call supply chain. And I think it's more appropriate to call it a supply tree. And as things go forward, the timeline, especially as the more complex the product you work on, the timeline complexity blows up really quickly. So imagine that if everybody's operating on this Amazon model where you talk to your supplier, they buy 10 lenses, and then they realize they're out of stock for the lenses or for the glasses, and then they need to go to the lens supplier, and lens supplier need to realize now I'm out of stock, I need to buy all those things. It's gonna take very many months for a complex project to complete, and that's why you need something called supply chain management. This is really a really important job, full-time job a person to not only talk to your supplier, but your supplier's supplier, your supplier's supplier's supplier, and then to inform them, okay, oh, I need this new part, or I need this new product, and I need a lot of them. So you give all of them heads up so that they can start ramping up all their production, and then they're all in sync in terms of schedule, such that eventually you can get the part you want at quantity. So to me, I think the analogy is kind of like a UV. Instead of where pip, you only fetch the first layer of dependencies. You look at all of your dependency tree and make sure everything is consistent. And the reason I spend so much time talking about supply chain is really this is something I learned the most about hardware, is that supply chain for hardware sometimes either equally important or even more important because it dictates whether you can make a buy versus build decision. This is a very similar decision if you're building hardware, software as well. So let's, can you hear me? Hello? Any question?
No, all good, all good. Very good.
All good? All right, cool. Yeah, so this is about buy and build decision. So if you have a good supply chain management, then you really can optimize what you need to build or what you need to buy. And a common mistake I see researchers going to hardware is that they try to build everything themselves, whereas many things are available out there. And then now, let's say we have all the parts. Now we need to actually build the glove. And then on the right, this is what we call skill capture glove. This is our data collection system derived from Umi. And this is the 1,000th glove we made. We painted gold. And really, the first step you need to do is assembly. So take all these parts, you put them together manually. For Umi, I have a video teach you how to do that. And then here, really, you need something called standard operating procedure or SOP. And then here, this is our lovely technician, Chris. And then here's a piece of paper in front of him. This is part of our SOP. And there's in practice many pages, and then it's divided across different workstations. And as soon as you start build something, if you try to build anything, really, you'll quickly realize you have some issue. Often it's about consistency. So if you want to measure anything, you build a camera, or to build an angle sensor, measure some reading, and then by putting things together, things are almost never consistent across different units. And so the first thing to solve that problem is to first identify each glove or each product we built. So here, we print a label that have a QR code for a serial number of this thing, and then inside the database we actually track all of the components. And then once you can identify a glove from another, the next step you do is calibration and QA. So these are often done together in software. So here, you really just plug in the glove into a computer, you perform a bunch of actions, and that records how the min and max range of each joint on the glove, and then use that you can calibrate the reading of the sensor, and also you can use this as QA. So let's say if you're moving the finger but the reading on the computer is not moving, something's wrong, or if the calibration range is super off compared to other gloves, that some mistake has been made. Then you need to either send the glove back to manufacturing, or you need to reject it. And again, when I talk about these things, it sounds very simple, but when you're making hundreds of gloves, thousands of gloves, it actually become a very, very challenging task. When human is doing any kind of work, you make mistakes, and then you can see when you build thousands of them, the probability of mistake is extremely high. And really here, I think like Henry is our founding software engineer. He built a critical tool. This is really to track all the data about glove in a software system. And there's a step after that where it's pack and ship. So you print a shipping label, you put everything in a box, and then you ship it out. So this entire process is called FATP. It's called Final Assembly, Test, and Pack Out. And this is probably when you hear about manufacturing, there's a company called Foxconn, things like that they do this kind of work for Apple. These are really, when people think about factory, this is what's happening in the factory. It's called FATP. And really, I think for this aspect, the biggest thing I learned is the power of software. So when you're building very complex hardware, there's a lot of moving parts. There's a lot of people involved. There's a lot of components. And in our case, the quality of this hardware being built directly impacts the quality of data that we can get. And therefore, it is very, very critical for us to be able to like have visibility to every aspect of this process. And that's why Henry built like actually he proposed to build the software for us like because he go to the eat dinner on the same table with people who put the glove together and then buy all the parts, and he also goes to the gym together with them. So he really is in constant collaboration with people actually doing the work. So he quickly realized that there's a huge bottleneck that's like slowing down our production. It's just that people, like the information are scattered around. People need to install these like random Python scripts here and there, and that really drives down efficiency. So what we found that in the end we're able to do is through the software, we're able to track every single component of the glove and who built the glove, when was the glove built, how was the glove calibrated, and then we can track it to every single piece of data that we collect. And then, so eventually, and this information is available all the way to our training data loader. Therefore, a researcher, if they think something sus about a specific kind of glove, they can just change a data loading config, and that will all be handled. So we found that this is actually very critical and in the end, a very impactful work. So I think my takeaway here is just that many times there exists a software solution for a hardware problem and vice versa. And often the solution and the problem space might not exist in the same domain. And that's why we need people who understand the entire stack or who understand multiple aspects to find the optimal solution. Yeah, so the next aspect we'll talk about is data collection. This will go less in depth, but I'll just really want to tell a few stories. So when we started, during my PhD, it's really about researchers collecting data. So these are my co-author Chur and Zhenjia both from Shuran's lab. So we take this Uni gripper, we go everywhere around Stanford or in Bay Area, we collect data and train a model. And this is I would say the easiest mode of data collection because everybody is a researcher, everybody can understand what it takes to train a model, and everybody understand have good intuition about how they collect data. The quality of the data directly impacts the end policy you want. But things get a lot more complicated when you need to scale data collection operation. So at Sunday, really, we have 3 generations of data collection owner. So the first owner was my co-founder Tony. He started out as a PhD student at Stanford, and he's now CEO of company. He started out as CEO of company, and he really go hand by hand, recruited the first 20 memory developers. These our terminology for data collector. And so it's about knocking on doors, about posting random posts on Craigslist, trying to find people to apply. And then after that, Camilla take over. Camilla, she already originally started as a campaign manager, for a political campaign, a local mayor for Honolulu in Hawaii. And then she became our head of operations and took over the data operation from Tony. And then she really scaled our data collection operation from 20 people to 200 people. And during this process, we need to things completely change. We need to formalize process of recruiting, formalized process of qualification, and then a streamlined process of shipping items out. But at this layer, she still can directly interact and understand every person who collects data. But eventually, we realized that model cannot scale beyond this number. This is for one person, this is about as much people you can keep in relationship as possible. So Perry is our right now current owner of our data. So he actually started out as a data labeler at Tesla for Tesla Autopilot, and then he grew all the way to leading all of the data labeling operation inside Tesla. And then now he's our head of data, and he's really growing from the 200 people that Camilla left, and now it's to 1,000 people that are collecting data for us every day. And one thing I really learned the most about data operations is that so when I started out, I'm a technical person, so I I want to write good code, write good user interface. I will say maybe there's some like AI generated instruction that can help people collect data more. But what I really learned is that data collection is an operation, and operations is really all the way about people. So if you understand people and you can build a good communication, can build good trust, then really you don't need much fancy software. Just a Slack channel and then some spreadsheet will be good enough for like let's say 200 people. But if you don't get the people part right, people don't feel like they're valued, they're respected, and they don't clearly understand exactly what you need and is actually what you don't want. Then actually there's no amount of software, there's no amount of technical work that you can fix that hole. And one thing we found really cool is that once people are really motivated, they understand like that they really want to contribute to actually make home robot reality. People start going all the way to help us. So when we started at Sunday, we actually in the beginning we're doing some kind of like Android phone-based tracking solution, and then it was like really not robust against white walls. So like one of our memory developer, he invented this method. He put sticky notes on the wall by trial and error, and realized that these can add features to the wall and can really help stabilize the system. Like really just being able to fully engage with the community of memory developers really help us early on when we started, when the technology is not mature. Yeah, so in the end, data is about people. It's like there's something about technology, but people is the most important aspect. I would say like the reason I put together these slides is that see the way I grew up and the way I learned robotics is that like my vision about robotics is all about algorithms. It's how can we make algorithms better, how we get a different paradigm of learning, different paradigm of data that is able to make robotics from not working to working, which I think is very important. But I will also say that the world is actually quite big compared to academia. There's many, in order to make something actually work in the real world, to build an actual product that some people actually use, there's a long way to go and a lot to learn beyond just what I learned in academia to what I actually what I need to do day to day. And that's what I think is like very, very fun and very interesting. And I wish I knew these things before I started the company. And like I wish there's a lecture like during my undergrad that teach me all these things. And that's why I'm doing it right now. And really during this process, I think I even have this idea during my PhD is that I think being able to operate across the stack is really, really important. So in academia, our education system is usually often structured in a way that's like vertically divided. So you are a mechanical engineer student, you are a software like a computer science PhD student, you're an electrical engineer PhD student, or in robotics you are a SLAM person, you are a learning person. But really, what I found is that to actually get robots to work, robotics is really in the intersection of every single engineering discipline. And many times a problem in one area requires a solution in a different area. And therefore, being able to have a visibility and intuition across the entire stack, from hardware to software to learning to data, really help you to find a good solution quickly and help you resolve issues quickly. And that's really the people we found. So I'm extremely fortunate to work with, I think now like close to 70 people at Sunday Robotics. We really focus on during our hiring and recruiting process on people who understand multiple disciplines at once. And what I found is that there's a commonality among them. It's often about passion and curiosity. So if someone's only like interested in like diving deep into one aspect, where they just want to follow the flow, like whatever school will teach me, now I'm a mechanical engineer, I'll just keep doing the same thing. Nobody's like our education system does not provide enough guidance on how to actually acquire all these breadth of knowledge. And what we found is that people who are really, really passionate about what they're doing and really curious about how things work, they will naturally kind of diverge from what they're doing as their main job to see, okay, they'll take apart like a clock, they'll take apart like a robot, and then they will really understand how things work underneath. And we found that these kind of like breadth of understanding is extremely critical to get robotics to work. And yeah, toward the end, so if you think you found like-minded people, you also enjoyed this kind of full stack development, or you aspire to become like a full stack roboticist, you want to understand everything, please check out our website. Yeah, that's it.
Hi, thanks for the talk. I'm pretty curious about your approach to locomotion, because a lot of companies like Figure and others are going for legged humanoids, and you guys have this rolling base approach. But again, like Sunday Robotics is targeting the home. Is your plan to move forward? Like, yeah, what's your approach to locomotion for houses that have multiple floors, things like that? Is it kind of like a proof of concept for now, or is it something that you guys are planning on working on?
Yeah, I think this is a very good question. I would say the way we think about like a problem and a big company is actually very different. Like a big company, they need to address the entirety market of humanity. Otherwise, it doesn't worth it for them. But as a startup, it's very important for us to focus on a small subset, like a niche category of people, and really satisfy their need. And we believe there's enough people where there's only one floor, and then they'll happy to buy a robot. And so for our very first product, we're definitely go with like the wheel-based approach. We think that's good enough. The robot is passively stable in any state. You cut power, it's not gonna fall, it's not gonna hurt anybody. I think that's a really difficult aspect to guarantee for a bipedal robot. So I would say eventually I think that's something we're interested in exploring. But I think before there's a consensus, what does safety even mean for humanoid in the home? And we'll be very cautious about that approach.
Thanks for a great talk and a very unique one on the full stack today. I had a question on the learning aspect and the data aspect that you spoke a little bit about at the end. You talked about the work that Perry and his team are doing in data labeling and data collection. Do you feel like human demonstration trajectories created by that team are sufficiently scalable for the learning that you're trying to do with your robots, or are you guys also exploring some of the recent directions that have been seen in video models and world models that try to learn from more internet scale data as well?
Yeah, so I can't say too much about our future research direction, but I would say even within the organization, how we collect data actually changes over time quite significantly. And then the kind of data we collect changes significantly. Really, everything is a variable. The only thing constant is the people. It's the same people collecting data, and people have the same need, same desire, and they're motivated by the same thing. And that's why I emphasize so much. Once you build a good intuition about how people operate, things become a lot easier.
I'm a really big fan of this method using the glove for extracting data. And what I'm really interested in is also when you said, okay, it's not just a question of software, it's also hardware and supply chain. How did you go about thinking, okay, these are enough degrees of freedom, these are enough sensors? For example, do you want to integrate tactile feedback to improve the policy? How many cameras do you have on your glove? That's a system-based question. How did you guys go about that when you designed the glove and the manipulator itself?
Yeah, very good question. I would say there's a couple of philosophies we follow. Number one, we follow simplicity is really the name of the game here. So hardware is not like software. Every complexity you introduce exponentially grow up in terms of probability of that causing a failure. So really we think that having the bare minimum in terms of complexity is key to actually ship something that's reliable. So in terms of when we started prototyping, it's really about our engineering intuition. So Tony and I, we did a lot of robotics during our PhD. We understand roughly what kind of geometry, what kind of degree of freedom is enough for the task we care about, and for what sensors we use. And then after that, it's all about iteration. So we have I think for the glove, we iterated probably 150 times of various versions of CAD. And you print a glove, you try it, you try on different things. It's really, it's a brand new thing. Nobody have done it before. So you just have to try a lot of things. And that's why I think having hardware and software and learning in the same, like under the same roof is so important. It's allow you to have a very, very tight feedback loop on your entire system, not just from each component.
When you're getting that much data from that many users, how do you maintain the data quality and like filter it? And have you ever gotten weird data from users?
Yeah, that's a very common problem. I would say, look, filtering, that's definitely very important. But I would say it's actually much more important for people to, like, number one, get clearly communicated of what you want, and to make sure what people, like, what they're trying to do is aligned with what you're trying to do. If everybody, all they're trying to do is to game the system, there's actually very, like, there's a million edge cases you wouldn't thought of. But if they understand that, okay, I want to use the data to help the robot to work, and these are the things, these are the aspects that a robot will likely care about. And these are like the impact of the data. I think people often quickly align with what we want to do.
Do you have time for one more question, or do you have to go?
Yeah, I have time.
Hi. What's your relationship with data collectors? Like, do you pay them? And like beyond that, how do you or Perry like motivate them to collect like more quality data for you? Like, how do you nudge them?
Yeah. So right now we pay them, and then I think that's very important. Getting other people's time, like you have to pay them. I would say. I think there are many attempts. I think in the industry of just collecting data in an unstructured way. I think those data are still very helpful, but often what you find is that the distribution you want from your data is not exactly the same as the distribution in the real world. Sometimes, pretty much, you want to do important sampling for aspects you care about. In those cases, you need to instruct people in a very detailed way. And what's the second half of the question?
Any motivation beyond paying them? What's the second part?
Yeah, I would say just there are people who stay-at-home mom. There are people who are very old people that like they just want to help their children for next generation. What I think is just that. I feel like a lot of people they understand that there's a wave of like AI robotics happening. A lot of them really want to be part of it, but they don't actually have like an entry for them to they're not like you guys. We're in this nice lecture hall. We can take classes, we can code, and we can understand how to help them. Like really, there are many people interested, but we need to explain to them what's a clear connection between the work they're doing. And like how does that kind of impact other people in the world? And we found that helping them build a connection to be very important.
Do you have time for one last question, or do you need to go?
Yeah, I have time.
Thank you. I assume that changing in the last year of your PhD, changing the university have had positive impact to attracting more investors, and probably it was the goal that you change it. And I was wondering, how was it possible, if I may ask? And yeah.
Oh yeah. Well, so I would say that's actually quite different. So that's my advisor changed university, not me changing university, and then she took me with her. So, I mean, I think I think PhD and undergrad are quite different. I think for undergrad, there are a lot of transfer opportunities. And I would say for PhD, it's much more about a specific advisor you're working with than the university. So when you see faculties move across different places, they often take the students with them.
Thank you so much.
Yeah. Cool. I think we are done. Let's thank again Cheng for his very insightful talk.